Okay.
Cool. Thanks, Ted. Next up is Larry Roberts from Anagran, who has a long history in the helping build the internet, and he's going to talk about IP fairness, changing the IP fairness rule with flow management.
Thank you very much. Welcome, everybody. I'm very concerned about the future. With one flaw, we've migrated into the internet. It actually wasn't there when we started, and it's turned into one that's fairly severe, and one that we need to take some concern over. I'll start, though, back at the beginning and talk about how the internet got started and where this came from. I started experiments in '65 between two computers to try and make sure what we needed, and we needed a new network. So then they drafted me into ARPA to build a network in '67. And as Vint showed you earlier, it got built with 4 nodes in '69. And we grew that through 1971 until I left in '73. The network was fairly large and was doing very well as far as a packet network, demonstrating the economic viability. Bob Kahn succeeded me in the office and took over in '73, and Vint Cerf was hired by him shortly thereafter, and they worked on the TCPIP protocol and got that established in 1983, and in 1986, NSF took over the network, and by 1991 it was commercially operable. So this is the growth of the network throughout that period. It was growing relatively slowly during the early period before we got a final protocol established, although TCP was under design most of that time. It got incorporated fully in '83, and the network grew pretty rapidly. Back in the early period, in '71, lots of things happened because we had the Aloha packet radio, and I then developed the slotted Aloha, which is now used for the Wi-Fi, and of course was used in the packet radio net, and also designed the protocol for the satellite network. We did a lot of different things. The Ethernet was invented during that period, and many different technological improvements occurred in packet technology in a very condensed period. At that point, things started, getting refined and built up, and the traffic started growing as TCP got introduced. In the beginning then, we had basically a single flow per person. In other words, voice, which was our main heritage at that time, was a flow per person, and we expected voice on the network. Danny Cohen did a lot of work on that and proved that it was going to be quite viable. And we were certainly considering that was one option and one use. We had, at that time, only terminal-to-computer activity in large part. It was designed to allow computers to talk with each other, but almost always it was one process talking to another. But mostly it was users in remote locations talking to one computer or another over the network. So it was one flow per user in each direction. So as a result, we sort of equated users with flows, and as the design never really was looking at fairness as an absolute issue, we knew users should be equal, and thus, as it came out that you had equal capacity per flow, that was fine under congestion. That was the concept that we allowed to occur, and it worked very well. Everybody got equal use of the network. Now, this is the overall graph of the growth. I've kept track of it for many years. In fact, I measured it very carefully around 2000, 2001 to see what was happening by polling all of the core ISPs, and found out how much it had grown. And similarly, people have published statistics all over the world since then, and we have a fair idea of what's happening overall. Over the same period from 1999 on, we've had P2P getting introduced, and it's consumed more and more of the network capacity. And that is measured pretty accurately by many people during the earlier periods up until a few years ago. And recently, those estimates have been declining, but that's because I believe people can't find all the P2P. The normal traffic at the moment is about a growth of two per year since the beginning of the network. So that is the overall growth. It's slower at the moment by quite a bit. The network itself is only growing at Moore's Law at the moment because fiber is makes communications capacity pretty cheap, and the electronic equipment is the main cost, and therefore, as electronics gets cheaper, you can keep the cost of the core of the network pretty constant. You're just adding edge nodes. And so the cost of the network is being constrained at the moment, partially because the normal users pay the bills, and they're not growing much at all. So where are we now? Well, the internet is still equal capacity per flow under congestion. They're not all exactly equal. They're all over the place, but they average the same over a period of time, so that they may stall and they may grow back, and they may grow back larger than anyone else, and then they may stall again, and then they may grow back. So overall, they're averaging about the same rate. The computers are generating the flows, not the users, though. So as a user logs into an application, runs an application, whether it's HTTP or FTP or P2P, he runs that application. The application does what it thinks is best in terms of the process. HTTP does tend to use many flows for the different parts of the thing, but not too many. P2P uses many flows and is talking to many locations, getting pieces of the video that it's downloading. So it tends to have a lot of flows. FTP could have a lot of flows, but it doesn't at the moment. We've actually tested that in some government experiments that have gone on, and that tends to work as well to generate more capacity per user. So in fact, if you do generate more flows, you get more capacity. And that is a problem in the network because you may have paid the same amount as your neighbor, but you can get vastly more capacity than your neighbor or your associate in the company or university. The congestion typically occurs at the edge, so that this is usually happening at a pooled point where you're pooling common capacity. It's not at your modem necessarily. You may have some pooling at your house, but it's mainly happening at a congestion point where the network enters the thin line going into the internet or the thin line going into a long-haul WAN link. And TCP generally expands to fill and cause congestion at these points because that's its goal, to keep on expanding. It can't expand generally past the delay limit, and depends on how far that's going and what loss it sees. But it will generally be able to expand to 20 megabits in reasonably short distances, and therefore you can fill up the link pretty quickly with TCP flows if there are just a handful of, a few hundred flows. That forces the equal capacity per flow. You may be running even at just 50% and peaking to 100 occasionally and not even see it at your 5-minute averages, but that still is happening, and you're still causing the equal capacity per flow. And then in fact, everybody gets about the same capacity per flow. And every user who paid the same gets different things depending on their flow count. This is more or less what it looks like on a typical home access. I don't think most people realize this at home. Most of you people do. But the problem is that the average user thinks he has the 10 megabits that I have out there for those 1,000 users. But actually, since the average is more like 100 kilobits per user, that's what the network is geared to. It may be 200, it may be 80, but it's in that range depending on the carrier. And it then narrows down to that bandwidth going into the internet. In fact, they don't need to offer more than that on average. On the other hand, if there's just about 0.5% to 1% P2P users, they can use up all that bandwidth. because they can generate enough flows to do that, and that will, in fact, they'll interfere with themselves if there's more P2P users than that. So anything above 1% or so will just be in excess of P2P, and they'll be competing with themselves. But they'll also have driven all the standard users way down in their data rates. This is what I see the network as in the last few years, and this is a linear graph, so you see the change more effectively. As I said, in recent years, people have been measuring it, and some of the DPI vendors have been reporting, well, it's down to 30 or 40% P2P. That's what they see. But in reality, there's a huge amount of unknown TCP and unknown UDP that, if you count it, shows that we're still running about 80% P2P. And the normal traffic is down, growing at only about 22% a year, which is significantly down from where it should be. And given the fact that you're being pushed down about 5 to 1 in your operating rate, then I would use about 5 times less or 3 times less. I mean, I wouldn't use more. I couldn't. It wouldn't be feasible. So I can easily hypothesize why the normal traffic hasn't grown that much. Now, this is a case where we have a gigabit feed into the internet and 100 megabits per user. That's like FDDI to the home, or a university with a gigabit feed into the network. And we've measured a number of universities now, and this is what we see. And the relationship is that even if you do DPI, you don't stop the thing at all. You have exactly the same total impact on the network. You're running about 97% P2P, and the normal user is being pushed down to a few percent of the rate that he could be running. And until you get to equalization, which is what I'm suggesting we move to, then you don't give the normal user what they expect, and the P2P would get the percentage that they get, which is whatever user would get. We can't get there by DPI. We can't detect it fast enough to keep up with the detection, with the encryption and the process of encrypting more and more. And in fact, the cat and mouse game is being lost slowly in that process. And it's not something that we can expect to win. So I'm proposing that we change the fairness rule. And we really never had one. We never created one as we created the network. We just sort of fell into the one I talked about because it seemed like it was reasonable when it occurred. And so inequity today is equal capacity per flow, and it's a huge inequity. And it will, in fact, get worse with time as more people try to use more flows to compete. And so P2P doesn't really know when to stop until it sees congestion, so it'll keep on adding flows until it does see congestion, and so you're bound to get to congestion, and you're bound to get to where there's lots of flows, as long as there's a number of people using P2P. Instead, we should, or any multi-flow technology, and I'm not discounting any other one because I think we'll start seeing many others pretty soon. Instead, we should give equal capacity for equal pay, or equal capacity per user if they're equivalent users, like all the students in a university. So this is simply a revised equity rule. Similar users get equal capacity, and that tracks with what we pay, and the network assures that all similar users will get equal service if there's congestion. And file sharing will find the best equitable method then, and it'll use the slack time, it'll use local hosts, it'll do anything it can to avoid hurting the network enough that it gets punished so that it can get the capacity it wants. Clearly, P2P can keep on running and keep on doing quite effectively, getting the same capacity as everybody else, but it can't overload other people at that point. So this is really a major worldwide problem. I've now heard from carriers all over the world, ISPs in every country, that this is so bad they may go out of business in some cases. The problem in Asia is even worse than here. The P2P isn't bad. It can be quite effective. It's actually a way to distribute files, but it isn't a good way if it grabs everybody else's capacity. But without revised fairness, multi-flow applications can take the capacity away from other users, dramatically slowing the network use for everybody, and it becomes an arms race, who can use the most flows. And that arms race is going to expand to include many other people. Uncontrolled P2P growth slows normal traffic, and the users get upset. This is a picture of what happens for the downstream path in an asymmetric ISP, where he's giving you 6 megabits one way, 3 megabits the other. That gives the P2P who likes to use the same amount in each direction, so it's using all of the upstream pretty much, except for the AX streams for the average users, and it's using that 50% of the downstream. But the AX streams of the average users are running so slow that they get slowed down with their normal traffic, and they can't run more than about 25% of the usage, and so you're now wasting 20% of the capacity. It gets worse if the asymmetry is higher. So the problem is that asymmetric operation actually is better than symmetric for giving people more downstream capacity, but it actually wastes capacity as well, and nobody gets to use it. This is certainly not the direction we want to go. Secondly, DPI has been used, but now the FCC is worrying about whether it's even fair to the P2P users, and it's not. It's attacking them even if they aren't using many flows, even if they're using just a handful, like the BBC in London. Unless it's a fair solution is deployed, service is going to deteriorate, and it's going to cause other people to go to multi-flows, like FTP using 1,000 flows. Why not? And UDP, and HTTP can easily send more flows, one from every sector of the page. Can send much more dense pages that way, much faster. So this can cause a major collapse of service. The uncontrolled P2P and multi-flow activity impacts to normal users if there's any congestion, and the P2P generally expands till it sees that, and so that's the case. And 50% average use, if you're running 50%, you're probably in congestion with the peaking. And the short overload periods cause the delay and loss and slowdown anyway, and that's where the P2P tends to stop. So that the average users run about the speed of the P2P flows, and they run very slow. This is a university case where they're running about 3%. 30 kilobits per user is not very much bandwidth to get. And until you're going down to 0.5%, you don't fix that. So this is a serious problem, one that can hurt everybody else. Even though you may find the P2P a reasonable and equitable and legal thing, it may be all of those things, it doesn't mean that it should hurt everybody else. We've got to change this, or the world will go further this way. So we need to resolve it soon. We need to any application that uses more flows, getting more capacity, it can hurt, and the capacity is often taken at the expense of others. P2P started to do this, and it's up to 1,000 flows sometimes. And in order to compete, other applications will do the same, FTP and HTTP. And UDP, without flow to control, could also be used to compete, but that's just one other case. There are many other things one can do to try and get the bandwidth one needs on the internet. One could change their TCP driver altogether to make one that was very aggressive. So in all those cases, the internet will be in trouble. We need to change the network to do this, because the user end will always be modified by the end user or used differently, and of course can be. So the revised fairness criteria that I'm proposing is equal capacity per user, or equal capacity for equal pay if the users are paying different amounts, instead of the current equal capacity per flow. That actually is a consequence of just discarding randomly when we have overflow, and TCP responds to that by slowing down, and the net effect is what I said. the fact that we can go to the other, it can easily be done with flow management or other techniques. I'm not specifying exactly how it has to be done, but we need to go to it in some way, shape, or form. It's not too hard to measure the capacity of each user and see what they're doing, and it's not too hard to then control their rate to a different rate if they're using more than somebody else. So today's technology really allows for us to do this and to have, at the choke points, the ability to manage multi-flow and any other inequities in the network and keep the multiple flows the same bandwidth as the single flow. And so everybody gets the same capacity through the network. This is not that difficult to achieve and is something which I really believe we have to work towards. And why is it important? Well, it's an attractive application. It can't determine a fair share itself, and the network must provide the boundary. Now, multi-flow applications are misled on economics. I've talked to lots of people now who are building new applications. They say, oh, I'm going to use P2P because it's a cheaper way to deliver software or cheaper way to deliver movies or whatever to my customers. And they don't realize that that's hurting everybody else and is their economics are badly misjudged. The cost of that to the community is very high. The cost of that last link is much higher than the cost of a server in the core of the network, which is connected to 10 gig things. In fact, probably about 20 times higher to get it from your neighbor than to get it from a server on the core. So it's really an uneconomic approach, but one that looks attractive now because the ISPs haven't put in this kind of new fairness. Once they do, then everybody will go to an economic structure and use what's most effective, and new users won't do things which are ineffective. Now, we can just monitor it, we can just look at it, and one technique that we've been using is to just watch for how many flows and how much traffic is there, and see if this persists for unusual periods. And you can very quickly detect detect the P2P users or the multi-flow users of any kind, and you can then send net flow records out for each of those flows and record those so that you know every P2P transaction that occurred, and you can record those fairly efficiently. And those records can be stored for any period if you want to be able to look back and see what happened in the past. All multi-flow users can then be clearly listed in a net flow collector. You can find out who they are, and you can do what you want to control the abuse. But it seems to me much more effective to actually introduce fairness so that people move in the right direction automatically rather than having to be disciplined. So in summary, what I wanted to get across is that P2P today adds flows until congestion occurs, and even if you reduce them to 0.5% from 5% with very efficient mechanisms, it still will congest the upstream to capacity, and everybody will suffer. The average user suffers major throughput reduction. This will get worse as many more applications use this, and in fact, as I said, we've already developed the capability in DARPA with a DARPA program to do this for other applications. And this will continue to happen if we don't change the mechanism and try to guarantee that people get equal capacity for equal pay rather than equal capacity per flow. Then users will get what they pay for, and 95% of the users will see a major throughput gain. In fact, probably 99%, because a lot of those current P2P users are being constrained by DPI. So everybody pretty much will win and get what they pay for on the network. This has to happen over time, or we're not going to survive, because as this happens, we're going to use up all of the ports in the network, and the ports are what we base net on, and net will fail. We can't keep on adding ports and adding flows. It just won't work in the long run. So we can't let this run out of hand and let the arms race go. We have to stop it somehow. So I really want to make a major statement that we've got to think about this, and everybody's got to help do this. in the network as fast as they can, correct the problem, and fix it. Thank you. Are there any questions?
Just a quick question. Are any attributions available for the graphs that you presented? What was the source for that material? Specifically, the traffic growth graphs, the percentage of traffic that's peer-to-peer, that kind of stuff.
That's a long process of collecting data that I've undertaken over time. Throughout the period of time the network was in the government's hands, I collected that data, and then in 2000, 2001, I polled every ISP under NDA because they wouldn't release it publicly. And so I got a clean set of data points for the traffic in that period. And since then, the US hasn't reported very well, but most other countries have. And I've slowly adjusted the US percentage based on the changes that I've seen and the numbers that I've seen overall. The P2P percentages have been measured all over the world at various points in time, and from 99 on through now. And so I've been collecting those measurements and looking at the fraction of P2P. The latest ones are based on my own hypothesis and the French study, which shows that they can't capture more than about 75% of the P2P. So that's fairly accurate, but can't be perfect because the US doesn't measure it anymore.
Hello.
In the original ARPANET, there were 8 bits for addressing, 6 for IMP and 2 for host. How did you arrive to those numbers?
The hosts and the numbers were kept track of by ARPA very carefully throughout its history. So those numbers.
1822 defined the 1 byte addressing. It probably was based on how many hosts you expected to have in some future.
Well, I can't change the numbers. Those are the ones collected. So it may have been inaccurate during that period, but it's not particularly, the traffic was measured as well. So I can't fix it, Danny. We can talk about it later.
Thank you.
I enjoyed hearing your presentation. I'm Tony Capella from 5.9's Data. And people call me the person who's interested in QoS, and it's kind of a dirty word. And I think what you've said here today tells me and encourages me, actually, in the sense that to manage things on a per user level, not a per flow level, we want to start looking at ways to perhaps deal with the congestion, the natural queuing that might have to happen here, that might need to be the result of managing perhaps a saturated DOCSIS media or DSL or interconnection between those devices. And starting to think about that in more than first in, first out would be a really good step from a vendor's point of view, I think. And I think what you're saying here, maybe you can agree or disagree, I'm curious about that, supports it.
Yeah, so that's the way I believe, that we can control individual flows, and that's the right way to approach the problem rather than discarding from a first in, first out queue. That's sort of a very random way to control the network.
Thank you.
Hi, Patrick Gilmore from Akamai. First, I'd like to say that it's a good presentation, and I think that everyone here agrees that well, maybe I shouldn't say everyone agrees, but I think it's a good idea to do it per user. But I had some questions. You were saying, on this slide, you're saying 0.5% of the total users can congest upstream capacity, and we talked about, or you talked about, a 6 meg down, 3 meg up network. That means that the upstream, which is half of the downstream, the network, which in the core and the peering is going to be perfectly symmetrical, does not have 0.25% available capacity, because half of 0.5%, the 3 meg versus the 6 meg would make it 0.25% of the total capacity. If 0.25% of users using the system can congest the upstream capacity, I think that there's a problem with the basic core design of the network to begin with, because even without P2P, you're going to run into problems. So, and earlier in the presentation, you were saying 5% of users are using P2P. I'm just wondering if, we already do some rate limiting per user. It's called the physical connection down the DSL line or the cable modem. if that's set up for only 3 megs upstream, and that is really being physically rate limited, because that's the clock speed on the piece of wire, shouldn't a normal network be able to support, 2.5% of their users actually using the bandwidth that they've given them? I think that sounds reasonable to me, but I'm wondering why you think that 0.25% of total user capacity can congest the upstream.
Well, actually, oftentimes people are sending and receiving at the same time. They don't have to be, but they can be, and that's encouraged.
Okay, so 0.5%.
But
one out of every 200 users
that particular slide should have been talking about 1% because of the limit of the bandwidth that was there. But some of the cases I've seen, and most of the cases I've seen, it's around 0.5%. So I used the 0.5% sort of widely in the 1,000 user case because that's what we tend to see. It depends exactly how your bandwidth is distributed and how big your pipe is, whether that's 0.5% or 1%. It varies.
I guess I'm just not disagreeing with the concept. I guess I'm just saying that if I were running a network and 1 out of every 200 users of my network doing something congested I'd feel that my network wasn't done right.
No, it's if 10 users out of those 1,000 are using 10 megabits, you've just used up virtually all your capacity. You don't have any more.
But that's not what you were. I mean, that's true.
But
that's not what you said earlier in the presentation when you had a much smaller much smaller megabits per user. But you're right. If each user has a gigabit, then obviously you have a problem.
They don't have a gigabit. They may have 10 megabits or 100 megabits. But.
Question over here.
Doing this side? Yeah, it's Brandon Butterworth, BBC. Adoption of the P2P was more based on enthusiasm rather than science. What we've found since is, although it might save us 6% our bandwidth, because it's download based, only half the people were watching what had been downloaded, so it was effectively wiped out the gain of using peer-to-peer. And since then, we've moved on to using streaming as well, and 90% of users prefer to stream a program, which has been half a bit rate of the downloads as well, so the peer-to-peer didn't really buy us very much, except quite a lot of servers.
Okay, I don't...
So I'm agreeing with you on it's not really all that is expected of it.
Right.
It seems like you could either focus a lot of attention on the CPU and the queuing discipline, or you could spend an equal amount of dollars and focus on just making the pipes bigger. It still strikes me that here in the US, we need much, much bigger pipes. And by focusing instead on the queuing discipline, aren't we trying to say, okay, we have enough bandwidth, we have plenty of bandwidth, let's focus on using it more efficiently instead of where we really ought to go, which is much, much bigger pipes.
Well, it turns out that if the ISP expands the pipe, he gets hurt much worse. That's what I was showing in one of the graphs. It goes from 80 to 99%. It gets worse because the P2P user can use more bandwidth, and they're able to use it symmetrically. It doesn't change the problem if you expand the bandwidth. The people with multiple flows will win still. And you can't expand the bandwidth as much as you might think to 100% because the core of the network just couldn't support it. We have 10 times the capacity at the edge or 100 times what we have in the core. The core just isn't going to expand that far economically in this day and age.
Would you say both solutions need to happen?
Oh, the expansion of the network is happening every day. As I say, it's currently going at Moore's Law as fast as people can build it. But it should be growing at a factor of 2, but it can't go much faster than that just economically. I mean, the core just has a certain limit in terms of investment, especially at today's prices. You want to take more?
Yeah, let's do a couple more questions. One down here at the end.
One of the questions I have is, in this model, how do you define a user? Is that by an IP address? Because there could be multiple users behind a NAT firewall, which I would say the majority of the network is based that way today.
Who are you and who are you with?
Jeff Turner with Interstream.
Thanks.
I am defining it as an IP address because that's what the traffic, the bandwidth is being sold to. So it's the per address is the only thing we have a contract with. and that's the one who bought the bandwidth.
Hi,
Right here.
Paul Mark, Petrus Nominum. I'm trying to understand what equal capacity for equal pay means. If I have two users in two adjacent houses on the same network and all like that, and one's going, you know, one hop away to another neighbor and goes as fast as he can, and another's going 5 hops away to Europe, how do I know when they're getting equal capacity for equal pay?
Well, the congestion point is really at the ISP's DSLAM or CMTS or whatever device he's using at that point. And that point knows what everybody's using, or it can be measured at that point or just adjacent to it. And you can see what everybody's using. Now, if he's going a long distance, he may not be getting the same bandwidth as somebody going a short distance, but you can also compensate for that.
So you're sort of saying equal capacity for equal pay in the local loop.
Right. If both people are paying the same amount, they should both be able to get the same capacity. There may be some inequities where they can't do anything about it, like if they're trying to go through a satellite hop. They just may not get the same capacity as anybody else. But that's because if they were doing the same thing, they would.
Thank you. Unfortunately, I think we got to get moving to the next one, and we have a break right after this talk. So why don't you find
I'm going to get you next time.
Dr. Roberts at the break. Thanks, Tony.
Thank you.
Thank you.